Congratulations, you have gotten to the more applications problem. If you are here and you do not understand what y equals a times b to the power of t is, I recommend you going back and looking at forms of exponential functions and their applications. It's really important that you're understanding that. I'm going to assume that you do in this video. So we've got a problem here and we're going to start looking at it. I like reading application problems all the way through before I start attacking them in order for me to understand what I'm being asked. So Arnold drops a bouncy ball from the railing on the second floor of a building. His measuring tool didn't reach the drop point, but that's okay. He collected the data that he could and would create an equation for the rest. So it looks like I've got a bouncy ball problem, which means that every time the ball bounces, it goes a little bit less high. I can see that here, 84.5 feet, I'm assuming, to 67 feet to 54 feet. So every time the ball bounces, it bounces a little bit less high. Thank you, gravity. That's what you're for. 0 is our starting point, the height of the dropping point. And 1, I guess, I'm assuming that 1 is missing as well because we don't quite know how much he didn't have a tall enough measuring tool again to reach that first bounce. So let's look. Our first question asks, what is the rebound rate? Rebound rate. I'm gonna rename that. I think that means growth rate. The rebound rate or the growth rate. How can I find this? Well, I know, because I know this is an exponential function, that to go from 84.5 to 67.6, that I have to multiply by my rate. I have to multiply by my rate. So I'm going to do a little bit of work off to the side. I'm going to do it in the upper right corner here of the screen. So 84.5 times my rate gives me 67.6. I'm going to use just Algebra 1 stuff to solve for my rate. I divide by 84.5, divide by 84.5, and I get my rate equals, and I can't do this in my head, so I'm going to use my calculator, 67.6 divided by 84.5. It actually comes out really nice. 0.8 is my rate. Well, rate is my b for my equation. So this rate that I now have, this rate is the same thing as my b here. Oh, man, that's really handy. So what is the height of the dropping point? That's a really challenging question to ask. So my rate, I'm going to write this in here, my rate, r, is 0.8. Well, I have two options now. I can go back here and say, oh, well, if to get down I multiplied, to get backwards I can divide. There's actually a very different way of approaching this type of problem to begin with. And it would be substituting values back into the equation. So I'm going to go ahead and do that off on the side. And I'm going to try and fit it into that little box there. So I know information here about when the bounce number is 2 and the height. So the height in my equation up here represents y. My t is my bounce number. So I'm going to plug in information for 2. So for the value of 2, when I have this value of 2, I'm looking right here. My bounce rate is 84.5 equals some unknown a times, I just found my bounce rate up here, so I'm going to plug that value in, 0.8 to the power of, we're thinking of our second bounce, power of 2. Okay, well 0.8 to the power of 2 can simplify into just a number. 0.8 raised to the power of 2 is 0.64. So I'm going to rewrite this. 84.5 equals a number, a, we don't know what it is, times 0.64. To solve for a, we have to divide both sides by the 0.64 and A is equal to, I'm going to put this into a calculator, 84.5 divided by 0.64 ends up being 132.03. Okay? So now we have the height, A, of our dropping point, 132.03. And we didn't even have to have a measuring tool to get up that high. We knew that from the previous bounces we could get there. What was the height of the dropping point? Okay, so now we can create our equation. We have our A, which is 132.03, and we can create an equation to figure out whatever bounce we want. Y equals our starting point, 132.03, times our rate, our B, 0.8 to the power of t, or the bounce number. There is our equation. Oops, let's make that a little bit nicer. Let's do another couple of problems because this was a lot of work to get there. In the early days of computers, viruses spread very quickly. In the early days of Microsoft software company, the number of uninfected computers was recorded in the table as the IT folks worked to stop the virus from spreading to all of their computers. How quickly are the computers being infected? What is the growth rate? So I'm going to think, oh, I have a value of uninfected computers. I'm going to multiply by that rate to get down. And this is a decay problem because the number of computers that are uninfected is decreasing, so my rate goes down. So what is my rate? My rate is 18 times R equals 12. Divide by 18, divide by 18. R equals 12 divided by 18. That's a terrible 8. It ends up being 2/3. You can hear my cat in the background. R is 2/3. So that's my growth rate. How many computers does the company start with before the virus? Again, we're going to use the information that we have from our equation that we like to use, y equals A starting point times B growth rate to the power of t, to determine this. I know a lot of information here about 2 and 12, so I'm going to use that plugging in values that I know. Y is the uninfected computers, 2 is the day number or the time that has gone by since this problem started. I'm going to substitute values in. 12 equals A, something we don't know, our starting point, times our growth rate, 2/3 to the power of 2, because we're thinking about day 2. We've got to go back here and know that our time is day 2 when we plug in that 12. So 2/3 to the power of 3. When I do that, I have to put parentheses around the 2/3. 2 divided by 3, close parentheses to the power of 2. And my calculator is giving me a decimal value, so I'm going to give it a decimal value as well. 12 equals A times 0.4444 repeating. To solve for A, we divide by that number, and I think that you know how to do that. A equals 12 divided by 0.444444 is 27. So my starting point is 12. That tells me what happens on day 0, 27 now. So I can, I've just answered this question. 27 is where we start. That's how many computers that we start with on day 0 before the virus has any time to spread. How many computers will be virus-free by the end of the 3rd or 4th day? So if we have an equation that models, how many computers are left uninfected computer, then we can solve. So we now know y of all the information we need to write an equation. Y equals the starting point. Well, we just found that out to be 27 times the growth rate, 2/3 to the power of the time that goes by. So if I want to find out the third day, I plug in 3 for the t. I plug in 3 for the t. So my y equals 27 times 2/3 to the power of 3. And when I put that into my calculator, I have to put parentheses around everything. So I put 27 parentheses 2 divided by 3 close parentheses to the power of 3. I recommend stopping this video and trying to see if you can get the same number that I get as well. It's really, really important that you know how to put this in the calculator. So on day 3, we get 8. On day 4, on the 4th day, y equals 27 times 2/3 to the power of 4 to equal, and I'm going to plug this into my calculator again. If you're struggling putting this into the calculator, try it out or ask someone for help. It's really important that you know how to put this in the calculator. My calculator gives me 5.333, which doesn't make a lot of sense. So I'm going to put 5.33 repeating, and we can let someone else figure out whether or not that is an important number. One more example problem that I want to make sure that you can do with us. These are very involved problems, and you really have to understand what this y equals a times b to the t means. In a small town, in a small rundown house outside of Tacoma, a population of killer bees has taken over. When the house was first monitored, there were 3 bees found inside. After 3 months, the house is checked again, and it's found that there are now 192 bees swarming on the property. Use the template y equals a times b to the n, where a is the starting amount, b is the growth factor, n is the time in months, and y is the total bee population, to find the growth factor for solving for b. Well, we have a lot of information. We know that 3 months there are 192 bees, and on the starting point there's 3. So I already know a lot about this information from my template. I know my current template looks, from the information that I currently know, y equals, my starting point was 3 bees. Was those 3 bees? 3. And I don't know what my growth rate is, times b to the n. But I do know what happens on month 3. So I'm going to start plugging values in. So this is kind of a temporary equation. I know that 192 bees exist. I started with 3 times some growth factor, I don't know, b to the power of 3. Well, this is super different than anything we've done before, but we can do it. Divide both sides by 3, divide both sides by 3. 192 divided by 3 is 64, so we've got 64 equals b, we cancel those 3's out, b to the power of 3. Well, I want that to be a 1. What do I need to multiply that by to get a power of 1? Oh, we know. We have those fractional exponents now. We can raise that to the 1/3 power. And I'm left, b to the 3 to the 1/3 is just b to the first. 64 in my calculator. Now this is a little bit tricky. We've got to put that 1/3 in parentheses. So I'm going to do 64 parentheses to the power of 1 divided by 3 in my calculator. 64 to the power of 1/3. The 1/3 has to be in the exponent. B equals 4. It's kind of crazy how we got it, but our growth rate for the factor of b's is 4. My equation, we now have all of the pieces to answer this second question. Write an equation that models this situation. Y equals 3, our starting point, times the 4 b's per month to the power of n, because we figured out that the 4 comes from here. This is a little bit complicated. Notice when we had b to the third power equals 64, to get rid of that third power, I just took the third power, 1/3 power on both sides, and I stuck it in a calculator to find this out. This is a little bit tricky, and it's going to take some practice. We'll practice it in class. You can ask me or others for how to approach this problem in the future, but now we have our finalized equation that models this situation. So I can find the number of b's after whatever number of months, or if I want to find a half a month, I can plug in half months in there as well. Thank you so much. These are very challenging problems. There's a lot of stuff to them, but I know that with a little bit of focus and you really understanding what this template means, you can understand how these problems work.